All right. So we're going to start now. Hi, everyone. Good morning. Thank you for being here. We're pretty happy to be talking about a research we did in the past few months about a UEFI rootkit we found in the wild. And what makes this thing very, very interesting is that it was actually the first one that was found in the wild. So we really found an infection that was and a threat actor that was using this UEFI rootkit to target their victims, right? So before we dive in, I just want to introduce ourselves. So my name is Jean Boutin, and together with my colleague Frédéric Vachon, we are both malware researcher. We're both based in Montreal. We work as malware researcher for a security firm called ESET, and we do malware research as a work, right? So we do reverse engineering mostly, and we try to piece together different campaigns. So if you looked at our title, you saw that we actually attribute this UEFI rootkit to a threat actor we called Sednit, but it also goes with different names. So we have Fancy Bear, APT28, Strontium, they're all aliases for the same group. And before we dive into the tools these guys are using, I just want to make sure that you are familiar with this espionage group. So just let me ask you a question first. How many people know of this threat actor? Okay, cool. So about half people, probably. So it's an espionage group. So they don't do cybercrime for really money. They do it to gain information on their victim system, right? They've been active since the early 2000s, and they were very visible in the past few years because they did some very notorious hacks. So I'm just going to highlight some of them. So maybe you remember the hack of the Democratic National Committee, or the DNC, that happened in 2016. It was leading to the US presidential election, and they compromised a lot of systems, and they were able to leak emails and leak them online, and a lot of people were seeing the conversation happening inside the DNC. The other act that happened recently is the World Anti-Doping Agency, or WADA. So these guys are allegedly behind these hacks. So they were able, again, to compromise systems, steal emails, steal information, and they also leaked it online. Under hack, since we're close to France here, maybe some of you know TV5 Monde, which is a French broadcaster that air programs throughout the world. And this group is, again, allegedly behind a hack, and they were able to cut their signal down for a couple of hours. And there's a lot of other hacks that these guys did. And I say allegedly because at ESET, we don't do attribution. So what we call the Sednit group is merely campaigns that these guys are doing or tools that these guys are using in their campaigns. But other groups actually try to attribute these attacks to a specific group. And there was something very interesting that happened last July, which is an indictment from the United States Department of Justice, where they were naming specific people, and they were, in this one, actually saying that these guys were behind the DNC hack. So this is, of course, another hint that these guys are linked to this. And why it's important for us is because they are actually naming a lot of the backdoors that the Sednit operators are using, and the backdoors that we are seeing that are targeting our customers, right? So this is another proof that these guys are behind these hacks. And there was another one quite recently in October this year, where they was also linking this group to the WADA hack as well as other hack, and naming people and naming the tools, the backdoors that these guys were using. So as the last step, I just want to show you how they are operating. So they usually use emails. So this is an example of a phishing email they would send to their targets. You can see here, the email says that your personal data has been found on Google, and then there's a link that if you click on it, you're not redirected to the real Google server. You're in fact redirected to a page that is owned by the Sednit group, right? This is an example of the type of phishing page that you would see. If the user goes ahead and enters their credentials, it will then be exfiltrated to the Sednit operators, which can then reuse them. Of course, they're not only using phishing emails, they're also using emails to try to distribute their malware. So they will have an attachment, a malicious attachment, that will try to install one of the various tools they use to spy on their victims, right? So you can think of backdoors, keyloggers, screenshot capture, all type of tools that allow them to know what is going on the victim and steal information from them. So this kind of brings us to our main topic, which is the UEFI rootkit. So not only are they have sophisticated backdoors that are trying to be persistent, but through our research, what we found is that they actually also have a very sophisticated UEFI rootkit. And not only they had this, but they also had the tooling to install it remotely on a computer. So of course, if you have physical access to the computer, it's actually quite easier to reflash the firmware to install these type of UEFI rootkit. In that case, as we will show you, they actually use a software tool to patch the firmware. So this concludes our little introduction. So what we're going to see today is first, what is LoJack? So I will explain why it's important to look at this anti-theft software. And we're going to take a quick look at the past research on insecurities and vulnerabilities that were found in this this software. And then we'll dig in the meat of the presentation, where how we found this UEFI rootkit. Also, we will show you the analysis of all the components, how it works, and also finally we'll do some remediation. So how you can protect yourself from this threat. So LoJack, it's an anti-theft software. It was known before as CompuTrace. Maybe a lot of people here know about this software. It's made by a company called Absolute Software, and it's present in a lot of laptops. So there's a good possibility that on your laptop you have this tool installed on your system. And what it does is that if your laptop is ever stolen or you lose it, it has different services to try to locate it using Wi-Fi signal or GPS location. You can also send different commands, so you can try to lock your computer. You can also try to wipe it remotely so that a hardware theft will not result into a data leak, and you can try to locate it through this software. And you need to activate it, and it's usually used by organization to make sure that they can track back some of their laptops should it be stolen, right? And there was a lot of past research on this. Why? Because of course, if you have an anti-theft software like this one, you want to make it as persistent as possible. So how these guys were doing it is that they had a UEFI module that will put back the agent if the thief would go ahead and reinstall Windows or replace the hard disk, let's say. So if they go ahead and do that while the system is starting up, their UEFI module was able to still reinstall the agent that could locate the laptop. So the first research that I want to show you is this one. It was presented at Black Hat USA in 2009. So as you can see, this is pretty old research, and I want to stress that out right now. Like, the vulnerabilities that we will outline today for this software is really old vulnerabilities. The newer version of the software does not have these insecurities built in, but still, as we will see, the old version were used to compromised systems, right? So in this research, they exposed design vulnerabilities in the agent and securities, and they also documented the architecture of the LoJack solution. And I want to show it to you because, as you will see later on, the Sednit operators actually mimic quite a bit the architecture that we'll see right now. So the first step is, of course, the BIOS or the UEFI module. So it contains the agent and its dropper, and it will go ahead and replace a file called autocheck.txt that is present on all Windows system. You might know what autocheck.txt is. It's basically an integrity check for your hard disk. So as Windows is booting up, you will see sometimes a percentage on your boot up screen, and this is this autocheck that will check the integrity. But what LoJack is doing is that it will replace it so that it can actually install its own agent, which is the second step, which is only the main idea is to install the small agent as a service. Once the service is started in step 3, you have the small agent, and the role of the small agent is to make sure that the full recovery agent is always running on the system. And how it does this is that if it's not there, it has the ability to connect to a distant server, download some code, and then execute it. So you can see right away the vulnerability that could happen if someone could actually control how the agent is where the agent is connecting itself to. And how it will do it is also very strange in terms of legitimate software, because how it will do it is that it will first spawn a service host process, then inject a DLL inside, then from there will spawn an Internet Explorer process, inject the DLL again, and we'll use this as a point to reach out to its distant server, which is not something we see regularly in legitimate software. In fact, this is something we see all the time in malware, right? So this is kind of a strange behavior for legitimate software. And then the last step, which is the fourth one, is a normal operation. The recovery agent is running on the system, and you have basically the mean to locate and recover the laptop. So you might wonder how the small agent is actually trying or to reach out to the server. How can it know the distant server domain name or IP address? Well, it has a configuration file embedded in its code. And this is the part of the small agent code that contains it. And it's encrypted. As you can see, we cannot see anything, but the encryption is actually pretty bad in terms of security because it's a single byte XOR key. So it's very easy to decrypt it. And you can see here the domain name, which is searchnamequery.com, which is the legitimate absolute software domain name that is used to send, that the agent will connect to and try to get will be able to have commands such as the log command that we've seen a bit earlier on. And the 4 bytes preceding this domain is actually an IP address. So the bad thing about this one is that there's no integrity check. So the file is not signed. So anyone that has access to your system and is able to override this configuration file can actually make the small agent connect to a server of its choosing, right? And I'm only showing this particular vulnerability to you because it's the only one that matters in our case, because this is how the Sednit operator actually did it. So although these vulnerabilities were quite old, so we saw the research was in 2009, we didn't see a widespread use of this vulnerability in the wild until May 2018, where the Assert team from Arbor Networks published this blog post, which was called titled LoJack Becomes a Double Agent. In this blog post, what they found is that there were a lot of small agent modifications in the wild where the attackers would change the configuration file to point to a domain that they own, an IP address. And what was very interesting is that these domains, these IPs, were already seen before. In fact, they were used by some Sednit tools. So that's what the first link was, that these small agent might be related to Sednit, right? So we saw this and we thought, okay, so what's the most likely hypothesis that this small agent would come in a system? And if we go back to the architecture slide, of course, SEP3 is a likely scenario where we already know that Sednit operators have a lot of backdoors at their disposal, so they could only use these backdoors to just drop the small agent. So of course, you don't benefit from all the persistence mechanism that the total solution of LoJack is giving you. You don't have the UEFI module, but since you're only changing a few bytes in a small agent and that it is legitimate software, you're still benefiting from the fact that a lot of AVs are actually whitelisting this small agent. So it's a likely scenario that they would just rely on a small agent and that's it. But at that time, we just dig in our telemetry and try to find out what exactly we could find and how big this thing was, right? So this is a configuration file that I showed you earlier, and what we found is that all these small agents that will link to the LoJack's campaign were based on the same small agent. So it was all a small agent compiled in 2008, and all they were doing was changing configuration file and a couple of bytes here and there, but in totality, the vast majority of the changes was only in the configuration file. But it allowed us to retry and do a wide spray and try to find who exactly was targeted. And we found some organizations that were targeted by this LoJack's campaign. So they were mostly in the Balkans, Central and Eastern European victims, and there were only a few organizations, and I want to stress that out because we know that Sednit is targeting a lot of people, a lot of organizations worldwide. But what we found is that it's only a subset of these targets that were actually targeted by the LoJack's campaign. It was mostly military and diplomatic organizations, which is in line with the target that that Sednit group usually targets. And what's interesting is that in all of these organizations, we were also able to find traces of other Sednit tools, which reinforces our thinking that this tool is really linked to Sednit. So we're now at a point where we're wondering, okay, like, is it the end of it? Is it only the small agent, or we're actually going to find something better, something more deeper than that, right? So before we dive in, I want to show you an interesting blog post which was published in Virus Bulletin by Kostin Ryu, the director of Great at Kaspersky, where he's saying that he's wondering where are all the A's in APT, and of course A mean advanced. And what he says is that there are many cool research going on in the security industry, and that no nation-state actor has actually used it. And one of them is actually this one, which is we have yet to observe a real-world UEFI malware. And it was funny because we were about to publish our report, and this is definitely something we knew that would probably be crossed out pretty soon. So before we look at the different tools that we found that led us to the UEFI Rootkit, I just want to show you this tool. So it's called Read Write Everything. It's a tool that is available online at readwriteeverything.com, and it's basically a tool that allows you to read and write. The name is pretty convenient. It allows you to read and write a lot of information about your hardware. So you have access to platform configuration, registers, and it gives you a whole lot of information about the hardware that your system is using. And how it does this? Well, it needs a kernel driver, right? And of course, when newer version of Windows all require the kernel driver to be signed. So this is the legitimate code signing certificate that is used by the kernel driver. And we found this specific driver in a lot of the networks that we investigated in link with the LoJack campaign. And it's funny because it's not the first time that this driver is reused for nefarious purposes, but in our case, it was really the first hint that they were really maybe after the hardware itself, the firmware. So the first tool that I want to show you is this one. It was called info.uefi.exe, and it's using the kernel driver, and it was just dumping a lot of information on the platform, logging it in the log file. Here I'm only showing a small excerpt of it, but the log file would be very big compared to that. And as you might know, if you are trying to target the system firmware, you need to have a lot of information, a lot of detailed information on the platform itself. So by running a tool like this, you get information on the manufacturer of the firmware, the motherboard, and it can allows you to see whether there are some known vulnerabilities and there are some misconfiguration that you can then reuse to actually patch the firmware. So if we go back to the architecture slide, so we already know that step 3 could have been what these guys were doing, just using a regular backdoor to install the small agent. But let's see what is the step before that. It's actually this autocheck.txt, so the executable that is responsible to check integrity, and that was used by LoJack, replaced by LoJack to install the small agent. So we went in and tried to find something similar, something that would tell us that these guys might be after the firmware itself, and we found an interesting file. So instead of being called autocheck.txt, it was autochi.txt. So only one letter changed, but the behavior of the executable was very similar. So you can see here it's installing a service with this name. So this is the same name that the LoJack solution is using as service, and it will then point to the location of the executable, the small agent executable. So from there, the behavior of this autochi.txt and the LoJack replaced autocheck.txt is very similar, but there was one difference that really caught our eyes, which you can see here. So it's building a string, and this string is actually the default value of this registry key, so the boot execute one that you see in the bottom. And this is actually the registry key that holds the path to the autocheck.txt. So we didn't know what was the value before that, but we know that this autochi.txt is actually putting it back to its default value, probably in an attempt to hide that it was ever changed, right? So that was, at that point, we knew that they were at least trying to get to the firmware, because you don't do all of this, you don't go through all these trouble if you do not have something in mind. So we kept on digging, and then we found the jackpot. So this is a tool called rewriter read.txt, and it's a tool that is used to dump the SPI flash memory and write it to disk, right? It still uses the read write everything driver and uses these 4 IOCTL code to write and read memory mapped IO, and also to read and write PCI configuration register. So the attacker will use this tool to dump the firmware of the machine. So we, of course, reverse engineered it. There were a lot of debug strings, actually. So it kind of indicates that this tool was probably under heavy development. But it also helps us, because as reverse engineers, you have debug strings. It makes your life a lot easier. So it consists of mainly 3 operations. So it will first log the information of BIOS control register. And Frederick will explain you why it's doing this and why it's important for the attacker to have this information. Then it will locate the BIOS region base address. and will finally read the UEFI firmware content and dump it to a file. So it does not have the capability to actually upload the file to a malicious server, but as Sednit operators already have a lot of different backdoors at their disposal, they could actually just pull the file out without the need for this tool to actually being able to communicate with a CNC server. And I just want to show you very quickly how it reads the flash memory. So this is very common. This is how you basically interact with the SPI flash memory. You first just initiate the transaction. You will say to the chip that you want to read it, how much bytes you want to read it, how much in the block that you want to read, and then you will just cycle through the whole memory mapped region and be able to recover all the firmware on the chip and then dump it to disk. So this is how this tool was working. So now Frédéric will talk to you about the other tool we found.
Okay, so another one of the tools that we found on some compromised machine is called RE-Writer Binary, and it is very similar to RE-Writer Read as its name suggests. So it also contains a lot of debug strings. It also uses RW Everything's driver, and it does basically two things. The first thing it will do is that it will add the UEFI rootkit to the previously dumped firmware, and it will write it back to the SPI flash memory. So let's look at the patching of the UEFI firmware. So before we dig into the subject, there's just a couple things here that I want to introduce, just to make sure that we're on the same page. The first thing I want to talk about is UEFI. So UEFI stands for Unified Extensible Firmware Interface, and it is a standardized specification that defines the software interface that exists between the operating system and the firmware. So a UEFI compliance system will provide a set of services to UEFI applications. Here read operating system loader. There could be some other UEFI application, but usually it is an operating system loader. So one of these services are the boot services. So these services are available to the firmware, but once the operating system is loaded, these services are not available anymore. And there are the runtime services, which are some other type of services that are also available to the firmware. But when the operating system is running, these services are still running. So a kernel driver, for instance, can make calls into these services. And from a security standpoint, what's interesting with UEFI is that there's no more master boot record or volume boot record involved. So there's no easy way to hijack the boot control flow. So, okay, the second thing I want to talk about are the driver execution environment drivers, so the so-called DEXI drivers. So DEXI drivers are PECOF images, so basically Windows executables, and they are kind of the core of UEFI firmware. So they can do many things. Some of them will be used to abstract the hardware. Some of them will be used to produce the UEFI standard interface, so the boot services and the runtime services that I just spoke about. And they can also be used by a firmware vendor to extend the firmware by adding, by registering new services, the so-called protocols in the UEFI specification. DEXI drivers are loaded during the DEXI phase of the platform initialization, and they are loaded by the DEXI dispatcher that we'll also refer to as the DEXI core in this presentation. The last thing I want to introduce for now is the UEFI firmware layout. So the UEFI firmware is located in the BIOS region of the SPI flash memory, and the BIOS region contains multiple volumes. So let's look at it in a bit more detail in UEFI tool, which is an open source tool for manipulating UEFI images. So here I loaded the typical content of a SPI flash memory dump in UEFI tool, and yeah, let's look at what we have. So the first thing that we see here is the descriptor region, which contains metadata about the remaining of the data in the SPI flash memory. Then we have the ME region, which contains the Intel Management Engine firmware. And finally, we have the BIOS region, which is really what we're interested in today. As I mentioned, the BIOS region contains multiple volumes. So let's look at one volume in a little bit more details. So here we have a volume, which is of type firmware file system v2, and so this volume contains multiple files. These files are identified by by GUIDs. That's what we can see under the name column. And if we look at what's inside a file, well, in a file there are multiple sections. One of these sections will be the actual UEFI executable image, but there are other sections like the DEXI dependency section, which allows to define dependencies for this specific UEFI executable. And we also see here a version section as well as a user interface section. So the user interface section is used to give a human readable name for the file instead of the GUID. And that's what we can see under the text column here. Okay, so now that we have all this in mind, let's go back to RE-Writer binary and look at what it does. So RE-Writer binary will parse all of the firmware volumes that it finds in the BIOS region of the UEFI firmware, and it will look for 4 specific files. It looks for IP4 DEXI, NTFS DEXI, SMI flash, and the DEXI core. So why does it look for IP4 DEXI and the DEXI core? Well, these files are used to find the firmware volume where to install the UEFI rootkit. So usually in a UEFI firmware, all of the DEXI drivers will be in the same firmware volume. So when the tool finds IP4 DEXI, it knows that it is currently parsing the volume with the DEXI drivers on it. So it will keep this volume as a candidate for the UEFI rootkit installation. And in some UEFI firmware, the DEXI core may be in a different volume than the DEXI drivers. So when it finds the DEXI core, it will also keep the volume where it is located as a candidate for the UEFI rootkit installation. And finally, it will choose the volume where there is enough free space available on it. So NTFS DEXI is the American Megatron Incorporated NTFS driver, and the reason why it looks for it is that, as we'll see later during this talk, the UEFI rootkit comes with its own NTFS driver, so to avoid any conflict, it just removes the American Megatron NTFS driver. And finally, SMI flash. So the version of the tool that we analyzed looks for this specific driver. It keeps some metadata in a structure about it, but it never uses it in the tool. So what we believe is that Sednit operator might have been fiddling with some kind of exploit for this. Well, what I forgot to mention is that this DEXI driver is actually vulnerable. So yeah, what we believe is that Sednit operator might have been fiddling with some exploit for this vulnerable DEXI driver in order to be able to bypass write protection mechanism to the SPI flash memory. So now that it has found the volume where to install the rootkit, the next thing is to add the rootkit to the volume. So what it will do is that it will create a firmware file system file header, and then it will append the rootkit file to it. So the rootkit file is a compressed section that contains 2 sections. One of these sections is the actual UEFI executable, and the other one is a user interface section defining the name for this rootkit. So the rootkit is called sec DEXI. And then it will write this file at the end of the selected volume. Okay, so now that the UEFI rootkit is inside of the UEFI firmware, the next step is to write it back to the SPI flash memory. Once again, there are a couple things that I want to introduce here. So I want to talk about bias write protection mechanisms. So the platform, read here, the chipset, exposes write protection mechanisms that need to be properly configured by the firmware, so there are no such thing as a write protection mechanism enabled by default. It's really the firmware job to configure them. Today we'll only cover relevant protection mechanisms to our research, so we'll only cover the protection mechanisms that are checked for by our RE-Writer binary. And the protection mechanism we'll talk about are exposed via the bias control register. So if you want to write to the bias region of the SPI flash memory, the first thing that you need to do is to set the bias write enabled field of the bias control register to 1. And then you can write to the bias write, to the bias region without any problem. But of course, you don't want any kernel driver to be able to mess with the content of the SPI flash and potentially corrupt it. So there's a protection mechanism here, which is another field in the BIOS control register, and this field is called BIOS lock enable, and it allows to lock BIOS write enable to 0. And this field is readable and write lock once. Write lock once means that once the firmware has set this, this bit to 1, there are no other way to set it back to 0 than performing a full platform reset. But there's a problem here. The problem is that the implementation of BIOS lock enable is actually vulnerable. So how it works is if BLE is activated and a kernel driver tries to set BIOS write enable to 1, BIOS write enable will be set to 1 for a short amount of time, and then the platform will issue a system management interrupt, and the SMI handler will set BIOS write enable back to 0. Let's note here that the SMI handler must be implemented by the firmware, otherwise this mechanism is worthless. But that's not the biggest issue here. So maybe you've guessed it, but what happens if we write to the SPI flash memory before the SMI handler sets BIOS write enable to 0? So there's a race condition vulnerability here. There's a paper about it which is called Speed Racer, and it is trivial to exploit. How you do it is you have one thread that continuously set BIOS write enable to 1, while another thread tries to write the data to the SPI flash memory. And according to the Speed Racer paper, it works on multi-core processors as well as on single-core processors with hyperthreading enabled. So Intel came up with a fix for this vulnerability, and what they did is that they added a field in the BIOS control register, and it was introduced in the platform controller hub family of Intel chipsets around 2008. So this field is called SMM BIOS write protect disable. The name is a bit misleading, but if you remove disable, that's actually what it does. So how it works is, if this mechanism is activated, it won't be possible to write to the BIOS region unless all of the cores of the processor are running in system management mode. And once again, this bit must be set by the firmware. Okay, so now let's go back to RE writer binary. So of course, if I introduce all of these mechanisms, it's because RE writer binary checks for them. So it will check if the platform is properly configured, and it implements the exploit for the race condition. Okay, let's look at the writing process decision tree. So the first thing that RE writer binary will check for is BIOS write enable. So it will check if it is activated, and if it is activated, there's nothing stopping it from writing to the SPI flash memory. So it will just write the trojanized UEFI image. But if it is not set to 1, then it will check is BIOS lock enable activated, and if it is not activated, then it will just flip BIOS write enable to 1, and then it will write the UEFI image. And finally, it will also check for SMM BIOS write product, and if it is not set, it will exploit the race condition that we just spoke about. Otherwise, it will just fail. So we spoke about the SMI flash, the vulnerable DEXI driver. So yeah, we believe that Sednit's operator might have been fiddling with an exploit for this specific driver to be able here not to fail if everything is properly configured, but to be able to write to the SPI flash memory, even if everything is the firmware does the job correctly. So this tool only works on either fairly old system or misconfigured system. So as you can see here, if firmware vendors would have done their job correctly, the tool would have failed at flashing the malicious firmware, and it would have required way more resources from the attacker's side to be able to deploy their rootkit. Okay, so now let's look very quickly at how you write to the SPI flash memory. It's kind of the standard way of doing this. So the first thing that you need to do is to set up the write operation, and then you can write you just loop around these operations and write each data block one after the other to the SPI flash until you have your whole firmware flashing to the SPI flash memory. So here let's take a step back and look at what we're looking at. So what we have here is a software implementation to deploy a UEFI rootkit and flash it to the SPI flash memory remotely post-exploitation. So that's really something, it's very convenient for the attackers to use that kind of tool. So they can just begin to infect the victim the way they will usually do it, for instance, by sending a phishing email. And once they have a foothold on the machine, they can use this tool to deploy their rootkit. What we knew about in the past was hacking teams' UEFI rootkit, and as far as we know, it required physical access to be deployed. So once again, it's so much more convenient to be able to do it remotely. Let's note here that there's no proof of hacking teams' rootkit being used in a cyber attack. It has never been found on a victim's machine, or at least if it has, it hasn't been publicly disclosed. So what we did then is that we extracted the UEFI rootkit from our eWriter binary, and we looked at ESET's UEFI scanner telemetry. And yeah, it turns out that we found the rootkit in the SPI flash memory of a system, making it the first publicly known UEFI rootkit to be used in a cyber attack. And at this point, yeah, we were pretty confident that we'd be accepted at Black Hat to share our research with you guys. So yeah, here we are, right? So if we go back to Kostin's Ryu statement where he said that we have yet to observe real-world UEFI malware, well, we can cross that one out. Okay, so let's go back to the technical part of this presentation and look at the UEFI rootkit itself. So the UEFI rootkit is a DXE driver that is loaded by the DXE dispatcher every time the machine will boot. Its file name is segdxe, as we've already seen, and here I put the file GUID for future reference. So now let's look at the UEFI rootkit workflow. So a UEFI firmware will go through multiple phases when it boots. So the first phase that it will go through is the security phase, and then it will go through the pre-EFI initialization phase, and then it will go through the driver execution environment phase, and that's when it gets interesting for us. So that's when the DXE core is running, and all of the DXE drivers will be loaded. So one of these DXE drivers will be the UEFI rootkit, and what it will do at this point is that it will create an event attached to the EFI event group ready to boot, and it will bind a notify function, which is basically a callback containing the malicious code. So when the firmware will go to the next phase, the boot device selection phase, the boot manager will run, and at some point it will signal the EFI event group ready to boot event. And at this point, the notify function will be called. So the notify function does three things. The first thing it will do is that it will install an NTFS driver. Then it will use this NTFS driver to drop AutoCheat.exe and RPCNetP.exe. And finally, it will patch a value in the Windows registry for persistent purposes. So the NTFS driver, well, the NTFS driver is needed to get file-based access to Windows partition. And Sednit operator did not write their own NTFS driver. What they did is that they took Hacking Team's NTFS driver from Hacking Team's leak, and they compiled their own version that they bundle with the UEFI rootkit. Now, here's the code responsible for dropping the two files. So here we have the code dropping RPCNetP.exe, and here the code dropping AutoCheat.exe. And finally, it will patch a value in the Windows registry. So how it does that is that it will open the file backing the HKLM system registry hive. And it doesn't have all the logic to be able to parse Windows registry structures. So what it does is that it will look for a textual pattern, and this textual pattern is autocheck star. And when it finds it, it will change it for autocheck autochi star. And it happens to be modifying the boot execute key that Jean spoke about earlier. So what will happen then is that the operating system will will be loaded, and at some point it will run autocheat.exe instead of autocheck.exe, and autocheat will drop RPC.NET-P, and so on. But what's interesting here is that autocheat revert back the modification in the Windows registry, so it will change autocheat back to autocheck, so that as a end user, for instance, if I look in the registry keys, I won't see that any modification happened. So yeah, it's a pretty interesting stealth mechanism that is enabled by the fact that the malware is coming from the firmware. Okay, so now we have a little demo for you. Just get there. It's not a live demo, sorry. Yep. I'll make it. There it is. Okay. Not really used to work with the trackpad. I'll just restart it real quick. Okay. So here we have a Windows 10 machine. This machine is clean, and it has a clean firmware. So the first thing I'll show here is just that autocheat.exe and RPC.NET-P are not on the file system, just to prove that it is clean. So it's going to syswow64 and looking for RPC.NET-P. And as we can hopefully see, RPC.NET-P is not there. Then I'm going into system32, showing that autocheat.exe is not there either. Okay, so the next step, then I'll go into a VMware directory to where the UEFI firmware is located, and I'll change the firmware, the clean firmware, for an infected firmware with the UEFI rootkit. So just to show that, I'm opening it in UEFI tool, and I'm just showing that segdec-cd UEFI rootkit is really in the UEFI firmware. As we can see, it is right here. And then I'll change the firmware. So this one is the clean firmware, so I'll just rename it, and I'll put the infected firmware instead of it. Okay, so now I'll just shut down the Windows 10 machine and start it all over again. Just so that the machine will boot and the UEFI rootkit will be loaded, and it will do all these nasty things. Okay, but here there's another machine, which is a Linux machine, which is on the same network, and it acts as a gateway for the Windows 10 machine, and also as a DNS server, and it also has an HTTP server on it. So I'll go in the Linux machine, and I'll start a network capture there. And then I'll just skip it a bit. So when Windows will be booted, we'll see that the malware will make a query to its command and control server. Should happen soon. Okay, so yeah, there was a DNS request that was performed for remotepx.net, which is the command and control server, and there was also an HTTP post request with the host header set to remotepx.net. So just to show that everything happened as expected, I'll go back in the Windows 10 machine and show that the files were properly dropped, and that there's also a process running there. So I'm going to C, Windows, syswow64. So I'm looking for RPCNetP here. So as we can see, RPCNetP is there. There's a DLL in executable. The reason for that is that the executable, once it runs, it drops itself as a DLL. So that's why there's another file there. And then, yeah, as we can see, AutoChi is there too, alongside AutoCheck. And finally, I'll go in the task manager just to show that there's a process running there. And yeah, as we can see, there's RPCNetP running there. So yeah, that's pretty much it for the demo. Okay. So the last thing that I want to talk about today is prevention and remediation. So what can you do to prevent such an attack from happening? And also, if you find out that you're compromised with a UEFI rootkit, what can you do, right? Okay, so prevention. The first thing and probably the most important thing is that you should really keep your UEFI firmware up to date so that all of the latest patches are available on your system. Yeah, so that's probably the most accessible and most important thing to do. Then you should enable secure boot, but let's note here that secure boot would not have protected against this specific attack. And the reason for that is that secure boot takes the content of the SPI flash memory as its root of trust. So everything that is inside the SPI flash memory is not subject for validation. So what is it used for then? Well, it will validate what's coming from outside of the SPI flash memory, namely the option ROMs, and most importantly, the operating system loader. So what can we do then? Well, what we need is a hardware root of trust. So we need a root of trust that is in a one-time programmable chip that is programmed during manufacturing time and that cannot be written to ever after. And such technologies exist. An example of that would be Intel BootGuard, but also Apple's T2 security chip has a hardware root of trust. Then you kind of need to hope that your firmware configures your the security mechanism properly. There's not much you can do. Well, if you updated your UEFI firmware, there's not much you can do. But thankfully, there are firmware security assessment tools available out there, and an example of that would be Intel ChipSec. So you can put this tool on a USB stick and run it on your machine. And this tool will check for all of the security mechanisms that we spoke about today, and even more of them. And also, it will check for this specific UEFI rootkit. So if you have it installed, Intel ChipSec will find it. And yeah, the last thing that I want to talk about is remediation. It's a pretty short part. The only thing you can do is really reflash your UEFI firmware, so you kind of need an SPI programmer, and to be able to, you need to have a clean version of the firmware and write it to the SPI flash memory yourself. It's definitely not something that is easy to do for anybody. But yeah, that's pretty much what you can do. Otherwise, if it's not an option for you, well, you can just get rid of your computer basically and get a new one. So that's how serious this attack is. Now, in conclusion, our research shows that UEFI rootkit are not toys for researchers to play with, but they are real-world threats used in actual cyber attacks. So it might be something that you want to keep in mind the next time you're defining your threat model. And yeah, we won't stress this enough. A firmware must be built with security in mind from the bottom up. And things are getting better because there are more and more security researchers looking into this and reporting the issues that they find. But there is still work to do there. And yeah, also hopefully this talk helped you to know how to prevent and mitigate this kind of attack. So that's pretty much it for us. So thank you for having us. The last thing I want to mention is that if you're interested to know more, to have more details about our research, the white paper is available at welivesecurity.com. And yeah, unfortunately, we won't have time for question here, but it's still early in the conference, so we'll be around for the next 2 days. So don't be shy, just come see us and ask a question if you have any. So thank you very much.